you. Thank you. Okay. So I think you can see my screen. It's okay?
Yes, that's okay.
Yeah. Thank you. Thank you for the invitation. So today I would like to talk about a recent project that we started at the Institute of Earth Science in Grenoble at InSAR. So it's a collaboration with PhD student Shan and Pierre and Virginie Pinel, and also some institutes that are strong collaboration with volcano observatories in Indonesia and in La Réunion Island. So here's just the outline of my talk. I'm going to just give you a brief context about why atmospheric correction are important during InSAR analysis, and then a bit of the method we used, how we produce InSAR delay maps from a GNSS local network. I'm going to talk about the criteria of evaluation we can put in place to evaluate the performance for the different atmospheric models. And then I'm going to apply this method to two case studies, so Piton de la Fournaise at La Réunion Island and Merapi volcano in Indonesia. I'm going to have a brief discussion about the impact of the correction on the detection of ground deformation signal. And then I'm going to give some conclusion and perspective of this work. So you are probably all familiar with atmospheric correction, but I'm just going to give a brief introduction. So usually the phase measurement that we derive from InSAR, radar interferometry, it's a sum of different contributions, and one of the contributions is atmospheric delay. And we need to correct this delay to be able to retrieve ground deformation signal, especially if this atmospheric noise is high. So there is two objectives on doing that. The first is on individual interferograms to prevent wrong interpretation during volcanic crisis. And also in time series, the atmospheric correction, if it's efficient, enable to decrease the detection threshold, and we can be able to detect small rates of displacement. For example, slow recharge of deep magma reservoir. So this atmospheric correction have been a major challenge in InSAR since the beginning. And here I just put you on the top left, an example of a RAP interferogram over Etna volcano that was interpreted initially by Masson et al. In 1995 as a deformation signal. Obviously, some other papers and scientists point out that this signal was correlate with topography and was actually most of the signal was due to atmospheric noise. More recently, there has been also some study that have misinterpreted ground deformation signal. For example, here we see on the bottom the example of Agung volcano. And we did a reinterpretation of the dataset, ELOS datasets for over Agung. So you see on the left panel, the loss velocity you derive, and we compare to a weather model, the loss velocity of a weather model that we'll describe later. And you see that there is a perfect match between the data and the weather model. And if you make the subtraction, you see that there is no strong signal over the volcano. So what can we do to correct and to mitigate this atmospheric noise for InSAR analysis? So most of the InSAR routine, the processing of InSAR use the two common weather model, ERA5 and GACOS. So ERA5 is 30 kilometers in spatial resolution and 1 hour temporal resolution. And GACOS is the model that's currently used, for example, for the LIXAR system by COMET, and is using a high resolution grid, about 10 kilometers, with a 6 hour resolution. In addition, the people also have used a lot empirical model based on the phase elevation correlation. It gives you a result very quick, and you just need the external DEM to compute this solution. Obviously, there is pros and cons for the different method. If you look on the right, for example, for the phase elevation, the major disadvantage is that you can remove part of the ground deformation signal, and that it only corrects the signal that's correlated with topography, stratified signal. For the weather model, the disadvantage is the low spatial and temporal resolution, and you're gonna favor or you're gonna correct mostly the long wavelength of atmospheric noise. So why not considering combination or both of the advantages of each method? This is what I did, for example, when I was in COMET. So on the left, you see an example on the top left corner of an interferogram, and you see that part of the atmospheric signal can be corrected by a phase elevation empirical model. And on the other way, a part of the signal that's on the coast, on the northeast coast, can be corrected by GACOS model. And then if you combine the two, you can arrive to reduce as much as you can the atmospheric noise in the data. So you need probably combination of different methods, for example, in this case. So here, I'm going to talk about AtmoVol, which is a 2-year project that was launched when I arrived at Easter. The idea was like, can we use local GNSS data that are available on volcanoes for improving InSAR atmospheric corrections? So I wanted to ask, to answer some of the scientific questions. Are the weather global model good enough for correcting atmospheric signal? And how the local models derived from GNSS data perform against this usual common global weather model? What are the factors that influence the quality of the correction? And can we detect subtle signal related to, for example, deep magmatic system? So here, just a brief introduction of how can we derive atmospheric delay maps from GNSS. So actually, each station, we can compute the zenithal tropospheric delay. That's the sum of the different contribution due to the constellation of the satellite. So you can project everything in the zenith, and this can be a hourly solution or even 5-minute solution, depending on the GNSS processing you are doing. So here on the bottom left, you see a time series over La Réunion Island for 1 year. And you see that is very scattered at the beginning of the year and low during the dry season here. This zenithal tropospheric delays, this total delay, can be decomposed in 2 components. The zenith hydrostatic delay here, that's mostly 90% of the signal, and it depends on the temperature and the elevation. It's usually calculated from a model. And then you can derive the zenith wet delay, which is 10% of the total delay, and mostly depend on the water vapor. So this is the contribution that's going to mostly affect the interferogram. And this is calculated as the residual between the total and the hydrostatic delay. It can be used also in atmospheric sciences for tomography of water vapor. So here I'm going to talk about Piton de la Fournaise, because it's a very active volcano, so we have a large number of eruptions, and because also it's a well-instrumented volcano. So here you see, for example, the last eruption in July 23 that produced fissure and lava flows on the Enclos Fouquet. So it's a well-instrumented volcano, so that was a good study case to start with. You see on the left here a map of the different GNSS stations in red. So you see the number of stations is about 40, and we have a large density over the volcano. For comparison, I also put the grid of the ERA5 and H resolution ECMWF. So you see that the GNSS station have a much better coverage and should perform better than the weather model. This volcano is very suitable also for this study because he has some InSAR monitoring since almost 20 years, and it's now part of a national service that perform the monitoring of this volcano using InSAR. Piton de la Fournaise is also a complex magmatic system. So if we look at the shallow depth above sea level, we have complex of sill intrusion and dike intrusion that's related also to a flank sliding. So there is an interplay between the magma emplacement and some flank motion toward the sea. If we go a little bit deeper, from 0 to 5 kilometers below sea level, we supposedly have a main storage zone, a magma reservoir. And then if we go even deeper, some seismicity also show probably some deep recharge from 8 to 15 kilometers deep. But we still have an issue because we don't really detect the ground deformation signals that are associated with this reservoir. So that's the challenge, and that's one of the objectives of the study, is trying to reduce atmospheric noise in InSAR time series and see if we are able to detect such a reservoir. So of course, the GNSS give you the ability to monitor the displacement, ground displacement related to the eruption. So here you see a time series of GNSS east-west, north-south, and vertical displacement on this station close to the summit. And you see the step related to the intrusion and eruption during the 21 year. Of course, this kind of signal of shallow intrusion are well detected by InSAR. So here, if we move now to the Zenith Tropospheric Delay that you can compute from the GNSS, here I show you an example for the Réun station that's located in the middle of the island. You see on the y-axis the hour, and on the x-axis the day of the year. So it's a 1 year time series over 21. And I compute the average hourly solution. So here you see one interesting point. You see that the hourly solution, it's kind of a sinusoid at the beginning. And if you compare to a 6 hour solution, so remember 6 hour solution is the GACOS solution that will interpolate linearly between these 6 hours. You see that you will, if you compute GACOS time series, you will overestimate the delay compared to the GNSS solution. Here, if you look on the right, the time series over a year, you see that we can really distinguish between the rainy season, there is a very high scatter delay, and the dry season when the delay is low and more stable. So now I'm going to move on and talk about the method we apply. So actually, we applied the same iterative tropospheric decomposition as Yu et al. In 2017 for the GACOS. So here you have, for each epoch, the zenithal tropospheric delay at each station over La Réunion Island. So you see here the values. It's around 2 meters. And what we do, it's first we compute and model the stratify components by an exponential law. So you see here the zenithal tropospheric delay as a function of the normalized elevation. And because we have a very good distribution in a different elevation, we can really fit an exponential law and retrieve the 2 parameters A and B. Using the DM, we then can compute the stratified component for the epoch 1 and epoch 2. And then if we remove the stratified components, we have a residual that we consider as the turbulent parts that we interpolate spatially using natural neighbor method. So here now we have a stratified map and a turbulent map for epoch 1 and 2, and we can just compute the delay map related to an interferogram by making the difference between the two epochs. So this is an example here on the left. This is a delay map derived from the GNSS ZTD that we can compare to the raw interferogram on the right. You clearly see there is a good correspondence. The amplitude seems okay. The pattern is retrieved. And then we can also identify some possible unwrapping error here over the cirque. So now we want to explore and see the performance over a 1 year data set, because here you can say, okay, maybe I show you only the case that's working, a very nice case. So I want to compute the ZTD over 1 year time series. So we use Sentinel-1 as InSAR data. The processing is made by LIXAR and NSBAS processing chain. We focus on 21, and we have 83 ascending and 108 descending unwrap interferogram. We will compare the GNSS model also to the ERA5 and GACOS model that I showed previously. As a criteria of performance, there is different way to quantify the performance of atmospheric models. We're going to focus on the reduction of the standard deviation, Q1, which is the relative difference between the standard deviation before and after correction. And here, a Q1 positive will mean that the correction is efficient, and we want to be close to 1 for the best correction. Here, I'm just going to show you individual interferogram. So here, it's an interferogram that very correlate with topography, as you can see with the DEM here, and compare the different model. The GACOS model on the left, in the middle, the ERA5 model, and on the right, the empirical model. You see that for a stratified model, as expected, the empirical model performed well and much better than the weather model. And now, if we compare to our GNSS solution, we can see that the GNSS model is able to retrieve the stratified components and do ever a better job than the empirical model. You see here, the final standard deviation is 1.2 centimeter for the GNSS against 1.5 centimeter for the empirical. Why so? Because the GNSS is able to retrieve the stratified, but also this negative signal here on the west and the positive signal here on the east. So there is a ramp. So it both corrects the stratified and a long wavelength from west to east. Here I'm showing you a more long wavelength signal over La Réunion Island. You can see there is a ramp from the west to the east. And this is actually correlated well with the cumulative rainfall. So this is cumulative rainfall over 21. And there is a dissymmetry in La Réunion Island between the west and the east coast. And this is something you can retrieve on interferograms. Here again, I show you the different models, and we see that weather model capture this long wavelength. This is not surprising. But if we look also the GNSS model, it gives you the same result as the two weather model. We can see that the final standard deviation is lower than the two weather model. So it gives a slightly better performance. But you see that the conclusion here is that in both cases, stratified and long wavelength, the GNSS model is a good solution. Now I'm going to move on to the statistic analysis, So here I'm just going to spend 1-2 minutes to explain this graph because you're going to see it a lot after. So it's giving you the performance, the global performance over 1 year data sets. So you have the Q1, the standard deviation reduction as a function of the initial standard deviation. So everything that's positive in this part of the diagram, it's interferograms with effective corrections. So I forget to mention that each point is one interferogram. And then everything negative, it's ineffective corrections. And I give on the right side, I give the fraction of the data set with effective correction. So here there is 40% of the whole data set that have effective correction. And you see here, this number represents the amplitude of the reduction. So we want to move as much as we can on the up of the graph, close to 1, to get effective and really good correction. So here I show you for the different model, GACOS on the top, ERA5 on the center, and GNSS for the 2 orbits, ascending and descending. What's striking is that GACOS is much less performant than the ERA5. You see a lot of ineffective correction in both ascending and descending, so negative values. ERA5 give like a 63 to 54% of effective correction. And here, if we move to the GNSS, we see that we are reaching 90% for the ascending and 78% for the descending. So we overperform the 2 weather models. There is a small fraction that's negative. And what we see here also is that there is always a better performance for the ascending track compared to the descending track, and this is probably due to the characteristic of the noise in the interferograms. So now it's important to understand if the different models provide an additional information, because if you want to merge them or to combine different models, you need to make sure that one brings additional information compared to the others. So what I did here is Venn diagram to represent that. So each circle is the fraction calculated for a model. So here, for example, the blue is GNSS, and it tells you that 90% of the data set has effective correction. We have on the top the ascending track and on the bottom the descending track. What we can see and observe from the Venn diagram is first that GACOS data, the GACOS circle, is encompassed inside the 2 circles of ERA5 in green and GNSS in blue. What does it mean? It means that all the interferograms that are corrected efficiently with GACOS are also corrected efficiently with ERA5 and GNSS. It means that GACOS doesn't provide additional information compared to the 2 others. And this is true for ascending and descending tracks. We'll also see that GNSS give a much better result or more performant result than ERA5, and only 2.4 and 5.5% of the interferograms are corrected by ERA5 only. So it means the ERA5 model provides only a limited additional information compared to the GNSS model. So now I'm going to move to the Merapi volcano. So the important to have this study case is to also look at another end members when you don't have a lot of stations. So I'm aware that the Réunion Island is a well-instrumented volcanoes. That will be the same for Hawaii volcano or the Etna that have a lot of stations, which means that you, of course, going to have a very good performance by retrieving atmospheric delays from GNSS. So I wanted to test also a case when you have only 5 to 8 stations, and this is the case of Merapi volcano. So Merapi is located in Java Island. This is a stratovolcano related to the Sunday Arc. And on the left here, you see the GNSS network. So there is actually 2 networks related to the Dome Merapi project and SATREP's Japanese project. So in total, there is only 8 stations. So I wanted to investigate what can we do with 8 stations. So here on individual interferograms, you see that on the left, a stratified noise on both Merapi here and Merbabu. And you can actually catch this signal with the GNSS model and perform as good as the weather model in this area. If now we look at an interferogram that have a much smaller atmospheric noise level, we see that GACOS and ERA doesn't really, or GACOS doesn't really catch this positive signal on the interferogram, the GNSS retrieve a little bit this stratified signal on both volcanoes, but you see that the final standard deviation is very similar to the initial one. So I did exactly the same and quantify the performance for the different weather model for Merapi volcano. And we see it's not surprising that the GACOS weather model in ERA5 do not perform really well on this volcano because they are better for correcting long wavelength. So you see that the performance of GACOS is 36% for the ascending and 41% for the descending. ERA5 is slightly better, 51 and 43. And now if we compare to the GNSS model, so I start by doing exactly the same methodology as the Réunion Island by combining stratified and turbulent parts. So this is what you see here on the left of each diagram. And you see that the performance are very low, 24% and 13% of the interferogram are well efficiently corrected. And this is because you see, if you try to interpolate spatially the turbulent components, the GNSS are only near Merapi volcano. So you're going to have issue with the interpolation. And this is what happened. So what we did is actually only consider the stratified components and not adding the turbulent parts in the final results. And what we get is 54 and 43% of performance. So we believe that when you have a small network, it's much better to only rely on the stratified component and not incorporate the turbulent one. Another test that we did is actually to restrict the area and only compute statistic over Merapi volcano because we know this is where we have information and where the GNSS are located. And if you do that, again, you have a very low performance, 27 and 10% if you consider stratified and turbulent. However, if you consider the stratified component, you reach 60 to 50%, which is similar or even slightly better than the ERA5 correction. We also performed the Venn diagram on Merapi area. So you see here on the left, and the results are slightly a bit different than for the Réunion Island case. For the ascending dataset, we can see that GNSS stratified model provide better performance than ERA5 and GACOS. So the conclusion is like you don't need a lot of stations to do a job similar to weather models. That's the first remark. Here for the descending data set on the bottom, we see that the performance are more balanced between the models. And actually there is 30% of the data set that is corrected by only one model. So that could be a case that you may want to combine the different solution or the different information of GACOS, ERA5, and the GNSS. So now I'm going to move slowly to the discussion part and what's the effect of this correction on the InSAR time series. So I'm going to go back to the Réunion Island. So here you see on the left, this is the velocity field for 1 year. So I took the year 2020. And you see before correction, there is a large uncertainty on the velocity field, but also you see that there is a large long wavelength pattern that's associated with the atmospheric noise in your data. If you perform the GNSS correction over all the interferogram and compute the velocity field, here on the right, you see that is much cleaner and you start to see some signal. We have some signal here, a small decrease of line of sight range. That's probably due to a landslide. We see also some signal here. And we clearly identify some very small scale signal over La Réunion Island. So if we take a closer look, here is the same thing on the left is before correction and on the right after correction. You see that on the left, there is still some atmospheric noise outside the volcano area. And the time series on the bottom is very noisy. For example, if you consider the points A, which is the reference in an area that's not deforming. If you compute the same time series on the right after correction, you see that you have a cleaner result. There is no atmospheric delays outside the volcano area. You decrease the noise level. So for example, if we take the point A as a reference, we have 2 centimeter noise level if you consider the 1 year time series compared to 3 centimeter before. You also see that you decrease a lot the rate of the point B, which is located at the summit of the volcano. So we had before correction 12 centimeter of subsidence, and then here we only reached 7 centimeter. And what you can see here on the time series, here I mark in red the eruption and in black the intrusion. We clearly see now that each time there is an intrusion or an eruption, a kink, like a small perturbation in the time series. That was more difficult to track and to identify on the left. We also see that between this intrusion and eruption, it seems that we have a clear linear pattern, especially on the point C, which is the sliding area that the flank that's moving toward the sea, toward the east. And we can really track now the velocity, the linear velocity pattern associated with this flank sliding. So there is a improvement of the information and the level of detail you can get at large scale, but also at small scale of the volcanic edifice. Okay, so now I'm gonna move to the conclusion, and more than the conclusion, some advices for correcting tropospheric noise on tropical volcanoes. So my first advice, if you don't have any GNSS station in your area, we recommend to use ERA5 models, because we saw that in Piton de la Fournaise and in Merapi volcano, ERA5 model perform better than GACOS. And we believe that is due to the temporal resolution of the model. It's better to have a better, higher temporal resolution, 1 hour, such as ERA5, than a better spatial resolution, at least in volcanic tropical environment. My second advice is, like, if you have a dense GNSS network, such as La Réunion Island, we recommend to use the total GNSS model that I show you, stratify and turbulent components, because compared to ERA5, you can gain, have an increase of performance up to 25%. On the opposite, if you have a limited number of GNSS stations, for example, 5 or 8 stations, try, and we can help with that. I will show you the next slide how. But you can have a try, because we see that in the case of Merapi, only 5 to 8 stations are able to gain and have performance similar to the ERA5 models. If you are interested in real-time volcano monitoring, GNSS models could be a good option. Why so? Because GNSS model can be produced in near real time. So in the case of Piton de la Fournaise, we can retrieve the ZTD 1 hour after, for example, the SAR acquisition. So we can produce the map of atmospheric noise as soon as we have the Sentinel-1 dataset. And this is not the case for weather model, when you can sometimes wait days to weeks to have the products. And then a bonus advice, if you do not have GNSS station in your area, you can maybe explore low-cost solutions. So for the ZTD solution, it has been shown that low-cost sensor can provide similar accuracy as permanent stations. And in the case of Piton de la Fournaise, there is some project that will try to put low-cost solution, especially in area that we don't have any station so far. And finally, this is my last slide. So what's the short-term perspective for this project? So we see here that the exploratory phase was a success. We really show that with GNSS, you can achieve a better performance for correcting tropospheric noise on volcanoes. And we have a paper submitted related to this work. Now it's time to move to the consolidating phase. And we have two objectives for the consolidating phase. The one is to release first an open source toolbox called Mongo for mitigating atmospheric noise using GNSS observations. And the second objective will be to test the toolbox on different settings, different datasets, different study cases. So if you are interested in testing Mongo toolbox, please contact me by email. And I think I'm done with my presentation and I'm happy to take questions.
Thank you, Fabien. That was a really interesting talk. We now have plenty of time for questions, so please put them in the Q&A. And I think Yasser has some to start us off.
Yes. Yeah, thank you, Fabien. It was very interesting to see how the GNSS model can improve the weather model results. So you had a discussion in your last slide. What is the minimum number of the GNSS data required to apply the GNSS model? You mentioned about the even with 5 to 8 stations, you can achieve some promising results. What about if for one case study for some small regions you have, I don't know, maybe 2 or 3 GNSS stations? Have you checked with the very small number of GNSS stations whether the GNSS model can provide good results or not?
Yeah, that's a very good question, and it's a question that I actually have had a lot during this project. So we are right now testing the network, testing the influence of the network, number of stations, and also distribution, because I don't think it's only related to the numbers. The first important thing is to have GNSS that have different elevation. So my answer is like, yeah, if you have 10 stations, but they are very in a narrow elevation, kind of the similar elevation in your volcano, of course, you're not going to catch the stratified component, and that will be an issue. So rather than the number, I think it's really related to the distribution, spatial distribution in X, Y, and Z. And we are trying to test actually the network influence. So by removing station and recomputing the statistic, we may have an answer to that. But yeah, I think the first, let's say, surprising result was that, yeah, with 5, it seems to perform as similar to ERA5 and even better than GACOS. So
yeah,
and yeah, that will be the second phase to test, obviously, more different network, different volcanoes, to see if we can get a better idea and more precise answer to that.
Yeah, and also in your results, you showed that the GACOS performance was lower than ERA5 in most case studies that you showed. Because initially I thought that because of the higher resolution of the GACOS data compared to ERA5, I would expect a better performance of the GACOS compared to ERA5. But how do you interpret this? I mean, based on your analysis.
I think it has to do, what I say in the conclusion, it has to do with temporal resolution is more important than spatial. Oh, okay. So if you see the daily average of ZTD, GNSS ZTD really show that is non-linear in time. So because GACOS is doing this linear interpolation between, for example, 0 and 6 hours in La Réunion, it will overestimate or underestimate many times the delay for the hour of the acquisition. So of course, it will depend where is your acquisition compared to the 0 and 6 points. But clearly, we show that there is a non-linear behavior, and GACOS. So I really also dig into some interferogram that have very inefficient GACOS correction. And what happened is, like, especially in La Réunion Island, because it's an oceanic island, that GACOS was anticipating an anomaly that was not there yet. So it has to be with the delay in time and the fact that you can get a very strong positive signal in GACOS model that's basically in the sea and not in the continent at the time of the acquisition.
I see.
And because it's changing very rapidly in oceanic islands. So I think the context of La Réunion also is what's make it very challenging for GACOS to correct artifact. Yeah,
that makes sense. Yeah, thank you. Thank you very much.
Okay, we have a couple of questions in the chat now. So we have two from Taha. The first is how changing reference points locations affect different models' performances.
Yeah, so I think the reference point is do not influence the result of the performance because we are looking the standard deviation of the global of the entire interferogram. So there is no influence of that reference point you are taking. So I will say that no, there is no influence. Your result will be exactly the same that of what I showed. Yeah.
Okay, and their second question is, why do the models perform slightly better for the ascending direction rather than the descending?
Yeah, so that's a good question, and that's something I try to answer and try to see why we always have ascending better than descending. And my answer to that is because it seems that it's appear in all the model. So you see that for ERA5, for GACOS, for the GNSS model, they are all different models, but they all correct more efficiently in the ascending. So it has to do with the noise, with the level of noise that is different between ascending and descending. So my understanding is like because you have maybe a more spread and higher noise in the ascending, statistically you have better chance to correct, to do a good correction because the signal is higher, the noise level is higher. So and the noise level is higher could be related to the time of acquisition. So for example, in La Réunion, descending and ascending is beginning and end of the day. So there is, of course, a difference of the atmosphere condition between ascending and descending. That's you can see on the noise level, and that's why there is difference.
Okay, our next question is from Milan, who says, what about if you just have one station? Can you foresee that you would use the ERA5 data to help get the coefficients and then scale using the station data?
Yeah, thank you, Milan. Thank you, Milan, for this question. So yeah, one station, obviously only one station, the method will not work because you won't have any correlation with topography for the stratified. So I will advise, of course, to use ERA5, but yeah, as you mentioned, so I haven't explored so far, but I think there is a way of improvement for GACOS and ERA5 if you can implement or if you can use the GNSS information and try to correct or to at least make a correction of if something is wrong in the weather model, one or two stations probably can help to improve. Usually, if we look at this weather model, they are based on data assimilation of different data sets, and obviously they take GNSS station when they are available. So that could be a way to do a data assimilation with all the GNSS data you get on the area to improve the weather model prediction.
Great. Our next question is from Ledong, who wants to know a bit more about the low-cost sensors. So they ask, can you talk a bit more about the low-cost sensor when GNSS is not easily available? What is measured and how much does it cost? What is the ideal density of deployment in comparison to using GNSS?
Yeah, so I'm not a specialist of low-cost GNSS. I thought it was important to say it at the end because I've actually had some discussion with people in France that are installing, and that is going to expand the network in La Réunion with some low-cost GNSS. But I can take some information and send it to you by email about the feasibility, the cost. This is information that I don't have right now, but I can look for it and yeah, share with you or directly contact the people that are more aware of that. But the good thing about low-cost GNSS station is actually it seems that the ZTD, so the tropospheric delay, that the accuracy of the ZTD is very similar to the one from permanent station. So for this application, that could be very interesting thing to do.
Okay, our next question is from Thomas, who asks if you have any thoughts on blending the ERA5 with GNSS results.
Yeah, exactly. That's so that's related to Milan's comment. I think there is a way of improvement to combine different kind of information. Right now, because I started with La Réunion, my thought was that you don't really need ERA5 for La Réunion, obviously, because GNSS do a very good job itself. But when we are moving to Merapi, we thought a lot about the strategy and what can you do if you fusion or if you merge these two results. So this is an ongoing this is the ongoing work actually, and we will try to investigate how can we, so data assimilation or using the GNSS to correct or to improve the retrieval of the stratified component can be one way. And then in the turbulent, we try different things actually. We try to use turbulent part of the ERA5 with the stratified derived by the GNSS, but it was not very conclusive when we did that. So yeah, we are still investigating if there is a better strategy than what we did so far.
Great. We have another question now from Milan, who says, you mentioned ocean island volcanoes as a challenge. Given that the models are not optimal there, do you intend to explore some new ways of empirical correction based on time series?
Yeah, so yeah, but I think there are studies that have been using empirical correction and PCA, as you mentioned, Milan, to try to mitigate this atmospheric noise, which works also pretty well. For the empirical correction, I'm always careful because you never know if you don't remove part of some signal, ground deformation signal, especially if you are not, if it's long wavelength. This is what we are looking for in La Réunion, actually. This is probably some small subtle signal related to deep magma reservoir. So if you are only looking the intrusion signal, which is very shallow, you will be fine and you know what you are looking for. But we are actually here trying to retrieve something we never detect before with InSAR. So I will be I will be skeptical to use empirical models in this case, because then you can remove this signal that you are looking for. So
okay. The next question is from Angeline, who asks what exponent is used for the stratified exponential law?
Okay, one exponent. So actually, we are retrieving these two parameters. So the two exponent, this is the unknown. This is what we retrieve when we try to fit an exponential law. So the exponential law is the ZTD as a function of the elevation, and then we get two components, two parameters, sorry, A and B, and then this we can inject in the DEM to have a map of the stratified delay. So yeah, this is an exponential law with two parameters that we retrieve from the fit, and then we use DEM to compute the map.
Great. Our next question is, does the ERA5 APS correction used integrated along the zenith and then projected along the line of sight? Because I think that if it's projected along the line of sight, the results could be better.
Yeah, that's absolutely true. So many people use this conversion of ZTD to loss, but obviously you should do a better job if you can project to the line of sight. And actually, the GNSS, you get also the information of the gradient. So you can use the gradient and really compute in the path of the satellite rather than the zenith. So I did some experiment with the GNSS, but my conclusion was that actually this effect is not big. It doesn't change much the result if you really consider the gradient and the line of sight projection, and this is mostly due to the incidence angle of Sentinel-1, for example. But if you compute that for another satellite with a larger incidence angle, something more like horizontal, obviously the effect will be bigger. So I agree that he has an effect to convert to zenith to line of sight. In the case of Sentinel-1, the difference were not very significant. But something to consider, and actually there is we are starting to work with La Réunion Island and with a PhD student that will start to compute the tomography of the water vapor from GNSS, and they are doing that, projecting in the line of sight directly the delay. So that's something we can compare what you can get.
Brilliant. Our next question is from Ronaldo, who asks, is there any way to correct wrapped interferograms for atmospheric contribution? And does this aid in the results when unwrapping the interferogram?
Thank you, Ronaldo. Yeah, that's a very good question, and actually this is something I have in mind. So we have a routine processing at ISTER, and actually we want to test that. So if you are able to compute the GNSS and correct the wrap interferogram before unwrapping, as you say, it can help to reduce the unwrapping error, and especially the one I show in La Réunion Island. We have very steep topography on the west on Piton des Neiges. There is strong unwrapping error always in this area because of the high frequency of the fringes. So clearly there is also a methodological development that use this GNSS model during the processing for improving unwrapping step, and then get a better unwrap interferogram and a cleaner time series. So we haven't done the job yet, but this is clearly on the to-do list for the future. Yeah.
Sounds good. We now have a question from Cindy, who says, would it be possible to implement a similar strategy to perform corrections due to ionospheric noise using GNSS total electron content data?
Yeah, so I haven't mentioned ionospheric noise in our study because obviously on volcanoes most of the time we are looking small scale, and ionospheric effect is much long wavelength. But this is something to look at. It could be a way, obviously, to use GNSS observation also for large-scale ionospheric correction. You might need, of course, a network that covers this a large area to be able to correct this long wavelength. So that will be feasible only in specific area that you have a dense and large-scale network. But something to look at, of course, yeah.
Okay, and probably our final question for today, which is from Hamid. When using GNSS on long-term interferograms to correct, should we also consider removing plate motion effect? And did you account for this in your methods?
So I'm not sure I understand correctly the question, but here we are not using the displacement, the information of the displacement of the GNSS, but the atmospheric delay. So I don't think, yeah, there is no influence on the plate motion on the values of on the information of the ZTD we get from GNSS. So I will answer no. There is no correction need to be done for correcting this effect, because we are just interested in the delay, in the tropospheric delay.
Okay, so we're coming up to the end of the webinar now. So I think we'll stop there, but I'm sure if anyone has any more questions, that Fabien will be happy to answer them by email. But before we finish the webinar, I want to mention the preliminary date of our next COMET webinar, which is the 24th of April, and will hopefully be given by Camilla Elizama at Leeds. But we're still trying to confirm the details of this, so please keep an eye open for future announcements. And in the meantime, many of the previous COMET webinars are available on YouTube. So thank you all for joining us today and for asking lots of questions. And thanks very much to Fabien for giving the talk, which was really interesting. So I hope to see many of you at the next webinar. Thanks very much.
Thank you, Isabelle and Yasser, for organizing this COMET Plus. And yeah, thank you everyone for attending.
Thank you, Fabien. It was great.
Thank you. Bye-bye.
Bye.